Questions about anything? Yeah.
We're talking about functions from R to R. Can we do analogous Fourier series for like functions from R2 to R?
Well, yes, there's questions about trying to do Fourier series on R2. There are multivariable versions of Fourier series. In fact, it's rather straightforward just to do them in each variable separately. And in fact, we'll do that when we do things like solve the vibrating square drum. So they're going to show up. But step one is to do them in one-dimensional case. Once you understand one dimension, the rest of the dimensions are very similar. Other questions? Well, at the end of the hour last time, I got kind of rushed and didn't complete this whole thing here. I was going to show you that the Fourier sine series and Fourier cosine series just pop out from the full Fourier series. So the sine series is on 0 pi. The full Fourier series was on a symmetric interval minus pi to pi, recall. And so here's how I did the sine series. I managed to get this done by the end of the hour. Suppose I've got that blue function, f of x, on 0 pi. Then I extend it as an odd function, so that f star is the extension of f to the interval minus pi to pi as an odd function. And then I write out the full Fourier series for that extension. And the thing we realized last time was that if a function is odd, all the cosine terms, those are the even terms in the Fourier series, are 0. So there's no cosine terms in that series. So that odd function, the Fourier series, on the whole interval is just the sum of the sine terms, bn sine nx. In those bn's, this is the formula for the bn's in the full Fourier series. It's a 1 over 2 pi instead of 1 over pi. Integral from minus pi to pi of the f star extension sine nx dx. And of course, f star is odd, because we made it odd, and sine is odd, and an odd times an odd is even. And now we've got an integral of an even function on a symmetric interval about the origin. So that integral from minus pi to pi is 2 times the integral from 0 to pi. And that gives us the same coefficient as for the Fourier sine series. And so this thing right here would be 1 over pi. And the interval is from 0 to pi, and so that's the Fourier sine series coefficient. So check. So that's how that works. So Bernoulli, of course, came up with the Fourier sine series before full Fourier series, but it can also be derived from the full Fourier series. And similarly, the cosine case, to get the cosine, I haven't mentioned cosine series yet, but it's the same idea. This time I have my blue f of x on 0 pi, and I extend it as an even function, which is an easy thing to do. So it's just reflecting it that way instead of twice. And then when you write out the full Fourier series for that f star on minus pi to pi, all the odd terms are 0, meaning all the sine terms are 0. And then when you write out the coefficient for the an's, you get an is, is it 1 over, it's 1 over pi times the integral from minus pi to pi of f star, which is even, times cosine, which is even, and an even times an even is an even, and so once again that's 2 times the integral from 0 to pi and that agrees with the, we don't know the cosine series. That's a new thing. That's the cosine coefficient term. And A naught is 1 over 2 pi, integral from minus pi to pi. And when I integrate that even function f star from symmetric interval minus pi to pi, that's 2 times the integral from 0 to pi. And so we get something new called the Fourier cosine series on the interval from 0 to pi. We can expand a function in terms of cosine. Interesting. We can either use cosine or sine to expand functions. That's pretty interesting. It's kind of like having 2 different bases for a set of functions. And that's exactly what it means. And notice that A naught, the new formula, is the average on 0 pi of my original function. And the AN coefficients look just like the sine coefficients. Let me just scroll back up and make sure I didn't screw up the sine coefficients. Bn, no, I'm sorry, I did screw them up. Bn is 1 over 2 pi, it's 1 over pi times the integral. And so this, to be the same as my Fourier sine coefficients, this needed to be a 2 over pi. There, now it's fixed. Sorry about that. Questions about that? Okay, that gets me caught up, and now I can start talking about today's subject, which is the complex exponential function, the most important function in all of math. I wrote it out last time. Today I'm going to do use this notation. I'll write z is x plus I, y. And today only, I'm going to write e of z equals e of z equals e to the z. And remember, that's equal to, so in the x plus iy notation, I wrote it out last time. That's, the real part is e to the x cosine y, and the imaginary part is e to the x sine y. Okay, and today I'll list the main properties that we care about for this course. Let's see. Simplest one is, call it 0 maybe. E of 0 is 1. 0, of course, is 0 plus 0i. Is a big fat 1. Okay. Another big property is that e to the z plus w is a product e to the z times e to the w. And interesting what that means from a group theoretic point of view. That means the complex exponential is a group homomorphism. Did I mention this in here yet? This is my other class where I mentioned that. So that's a group homomorphism. If you take a fancy algebra class, you'll talk about such things. It's a group homomorphism from the additive group on C to the multiplicative group. Let's see, the multiplicative group, 0 doesn't have an inverse. So the multiplicative group is on C minus the origin. Sometimes that's called C star. And in fact, that's kind of a unique thing. So in fact, being that group homomorphism pins down the complex exponential. Let's see. So once you play around with this number 1, then it's easy to get a number 2 here. Let's see. E of z minus z. That would be E of 0. Let's see. Let me do it like this. 1 is E of 0. And of course, that's E of z minus z. And that's e to the z times e to the minus z. This shows that neither one of these things can be 0, because they multiply together to be 1, which is not 0. So we see from this that e to the z is never 0. Is never 0. And we also see that e to the minus z is equal to 1 over e to the z. As a complex number, because their product is 1. Of course, then if I have two complex numbers, e of z minus w is e to the z divided by e to the w. Oh, a couple more things maybe. E to the x, when x is real, is e to the x plus I 0, plus 0 times I, and that's e to the x times 1. Cosine 0 is 1, and sine of 0 is 0. So that's e to the x. This shows that e to the z extends e to the x, the real version, to the complex plane. So e to the z extends the real version, e to the x, to the complex plane. And in fact, it's the unique thing that does that in a complex differentiable way. And I guess as long as I'm doing famous formulas, e to the iy is Euler's identity. That's cosine y plus I sine y. Let's see, so all these things follow from the which one? Number 1. So I'm going to demonstrate number 1 from first principles. And all the rest followed. So that's the only thing I have to check. So let's see. Proof of number 1. Turns out it's just a trig identity. So e to the z1 times e to the z2, that would be, let's write it as e to the x1 plus I y1 times e to the x2 plus I y2. That would be multiplying complex number e to the x1 times cosine y1 plus I sine y1 times e to the x2 times cosine y2 plus I sine y2. And you know the order you multiply complex numbers in doesn't matter. They're associative. So I can put those two e to the x's together in front. And then when I multiply the rest of the junk together, let's see, I'd get a cosine y1, cosine y2. The other place where I get a real number when I multiply those two is when the I hits the I in front of the sine functions. And so that would give me here a minus. That's the I squared. Which is minus 1. That would give me a sine y1 times a sine y2. Then the imaginary part would be I times, let's see, I'd get a cosine y1, sine y2 cross term, and I get a sine y1, cosine y2. Why don't I do it like this? Cosine y2, sine y1. And those should look familiar to you. Those are the famous formulas you learned in trig class someplace. This is sine y1 plus y2. And this one is cosine y1 plus y2. And of course this is e to the x1 plus x2. We know that basic property of the real exponential. And so when you look at that for a second, you realize, aha, this is equal to e of x1 plus x2 plus I y1 plus y2. Check. Now that you know this is the true thing, that's exactly how I can derive the trig identities for sum of angles just by multiplication. So I flush those formulas from my memory. So here's a remark. Easy to deduce or remember. Sum of angles formula. Formulas. All you have to do is do e to the I alpha times e to the I beta equals cosine equals e to the I alpha plus beta. Write those out in terms of cosine and sine, equate the real and imaginary parts, and so use Euler identity. Multiply out. Equate real and imaginary parts. And there they are. Euler identity. Questions about that? Well, this leads to a famous formula called de Moivre's formula, which is very useful, especially in Fourier series here. And it is that e to the I theta to the nth power is e to the I n theta. This is the thing you used in high school to find nth roots of complex numbers. And that's, of course, cosine n theta plus I sine n theta. Those things on the right are short and sweet compared to multiplying that thing out on the left n times and thinking about what kind of a mess you would get. Get all kinds of trig identities when you start playing around with that. And this is true for n, which is any old positive integer or even a negative integer. So this is true for n in integers. And this was an important tool for computing the nth root of complex numbers, which I won't be doing today, but for finding all the nth roots. There's n of them, of course, of a complex number. Let me prove it. Let's see. Let me prove this for the n equal positive case. So n, a natural number, 1, 2, 3, 4, 5, 6, etc. Well, then we would have e to the I theta n. Property number 1 would say that that's e to the I theta times e to the I theta n time. Well, let's see. That's what the nth power means. This is n times. And then I would use property number 1 on the first slot and get an e to the I2 theta. And then I would do it on the next slot and get an e to the I have e to the I2 theta times e to the I theta. That would give me an e to the I3 theta. And I do that again and again, and by induction, the last time, I'd get an e to the I n theta. So so that would be e to the I theta plus theta plus theta. I do it in stages. There's n of those. And that's e to the I n theta. Check. And now that I know it for positive n, I use that for negative n. I have this identity here, and I would just apply the fact that I know that e to the minus I theta is 1 over e to the I theta to the above. That's all there is to that. I guess this isn't 425, but if this were 425, this is where I'd start trying to convince you that the complex exponential is complex differentiable. So here's a fun fact. E of z is complex differentiable meaning that the limit, you take a difference quotient, limit as z tends to a of the complex difference quotient, that would be e of z minus e of a over z minus a, exists. And since it does exist, we call it e prime of z. Well, let's see. That would be e prime of a right there. And a fun fact is the complex exponential is its own complex differentiable. So here's a big one. A big property. e prime of z is itself, just like in the real case. So this complex valued function has a complex derivative, and it's its own complex derivative. And when you combine that with the initial condition that e of 0 is equal to 1, these two things determine the complex exponential completely. These determine e of z. It's the only function with that property. Well, figuring out the difference quotient for the exponential would be a new feeling. It's not exactly like freshman calculus. I guess an example I should show you, the difference quotient for z squared, for example. That would look just like freshman calculus. That would be z squared minus a squared over z minus a, and you can factor that top to be z minus a times z plus a, and the z minus a's cancel, and you realize, just like in freshman calculus, as z tends to a as a complex number, that tends to 2a as z tends to a. So you think, oh, complex calculus is going to be just like real calculus. It's just the numbers are going to be in the complex plane. When you start thinking about e to the z, you've got to do more work than you do for the real case. It's not hard, but it would be an interesting subject. So interesting it would make a good course. Okay, well, one reason I'm getting going on the complex exponential is because we're going to need it when we do Fourier series using the complex notation. And one important reason we do that is because of this function I'm about to write out. So a very important function in the subject is the Dirichlet kernel. Dirichlet is in my family tree. If you go back and look at go to my advisor, back, about 14 generations, you come to Dirichlet. He's a couple generations down from Bernoulli. So this is called the Dirichlet kernel. And the notation for the Dirichlet kernel is a dn of t. Sometimes they put a 1 over 2 pi in front of it, sometimes they don't. I'm going to make my notation short and sweet today. So let's see, it's the sum as little n goes from minus capital N to plus capital N of e to the int. That's what it is. I want to write that out now and play around with it. That's, let's see. Let me do the negative ones first. That would be a sum as n goes from, here's the negative ones, 1 to capital N of e to the minus int. So those are the negative ones. And then I need the 0 to the positive ones. That would be a sum from 0 to capital N of e to the int. Okay, and that is, let's see, that's the sum as n goes from 1 to capital N. Cosine minus nt is cosine nt, because cosines are even. And the sine one is negative. Sine of minus nt is minus sine of nt. Okay. And let me put the n equals 0 case here. That's the n equals 0 case. And now I'll put the n equal this is the easy one. E to the int is cosine nt plus I sine nt. Well, look at those. The minus sine t on the first sum cancels the plus sine nt on the second sum. So that Dirichlet, that thing, looks like it's going to be a complex function, but it boils down to 1 plus 2 times the sum from 1 to capital N of cosine nt. So it's a sum of wiggling cosine terms. And I claim that this is going to be, even though it looks like it's a mess, by using the de Moivre's formula and playing around, this is going to be equal to sine of n plus a half t over sine t over 2. Incredibly simple thing for a sum like that. So it looks like it's going to wiggle like crazy and be a mess, but it's actually kind of a clean function to look at. The graph of that thing is a beautiful thing to look at. Okay, that's the famous formula. Let me explain why. It's going to be easy. It's going to be just geometric series. So let's see, the thing I want to play with, it's kind of like your homework problem. I'm going to look at 1 plus cosine t plus cosine 2t plus out to cosine nt. That's the real part of 1. 1 is real. Cosine t is the real part of e to the it. Cosine 2t is the real part of e to the I2t, etc. And cosine nt is real part of e to the int. And then you look at that for a second and realize that is a geometric series because of de Moivre's formula. That's 1 plus e to the it. E to the I2t is e to the it squared plus dot 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 plus e to the it to the nth power. A geometric series. And the thing you learned in junior high school or someplace about summing a geometric series works just fine in the complex setting. So let's think, let me see. That's a geometric series, exclamation point. And geometric series satisfy this famous thing. Let's write S sub n is 1 plus z squared plus etc. plus z to the n. That's the nth partial sum of the geometric series. And you learn that if you multiply that by z, it just shifts it to the right. So the first term would be z times 1, that's z, plus z squared, etc. Z to the n would still be there, but then you'd get this thing hanging out the end here of z to the n plus 1. And you realize if I subtract those two things, the sum of all that junk in the middle would collapse out of it. So I take this, I subtract, and on the left-hand side, I get 1 minus z times the nth partial sum equals, on the right, all that stuff in the middle cancels 1 by 1, and all I'm left with is 1 minus z to the n plus 1. So the nth partial sum, I suppose I should call it Sn of z, is 1 minus z to the n plus 1 over 1 minus z. That's worth putting in a red box. And so my cosine, let's see, remember back to my cosine calculation. Let's see, I should go back up. Where was I? Let me call this star. So this thing right here is star. Star is the real part of that mess. And now I've got it expressed as a sum of a geometric series where the z is equal to e to the it. It's a complex number. And so down here, I would get that star is equal to the real part of 1 minus e to the it to the n plus 1 over 1 minus e to the it. Okay, let's see. I'm going to give myself some space. Let's see. I guess I'll rewrite it. That's equal to the real part. I'll keep the bottom the same. And on the top, let's see, I can use de Moivre's formula. That's e to the I n plus 1t. And I want to make the bottom of that thing real. And I'm thinking of the cosine and sine functions I learned last time. I want to turn that bottom thing into I guess it's going to be a sine function. So in fact, I'm going to multiply the top and the bottom. Let's see. E to the minus it over 2 is going to make that pretty much the sine function in the bottom. And so if I do that, I have to do it on the top and the bottom. And let's see, I want it to be the sine function. So let's see, e. So it's going to actually be the sine function. I'm going to have to multiply and divide by minus 1 over 2i. Because the sine function had a 2i in the denominator. Okay, so that's going to give me, when I do this, something real in the denominator, which is going to be convenient. Let's see, what's it going to be? E to the I t over 2 minus e to the minus I t over 2 divided by 2i. And on the top, when I'm going to collect all the junk and skip the details. The top, when I multiply those out and use properties of complex exponential and use the fact that 1 over I is minus I get I over 2 times e to the minus I t over 2 minus I over 2 e to the I n plus a half over 2, no t. Okay, and the exciting thing here is that this thing on the bottom is sine t over 2. And the real part of that, not hard to spit out, is equal to something short and sweet, namely 1/2 sine t over 2 plus 1/2 sine n plus a half t, all divided by sine t over 2. When you write it, so I would write out that top and collect the real and imaginary parts and realize it's not as ugly as it looks. Well, that sine t over t 2 cancels there, and it looks like I'm getting close to the Dirichlet famous formula. 1/2 plus 1/2 times the thing I'm shooting for. Okay, so finally, when I want the Dirichlet formula, so wow, that simplifies. I can't help but say wow. That was a sum of n things. It all simplified down to something very simple and clean. And the Dirichlet, even a better miracle happens with the Dirichlet kernel. Remember, the Dirichlet kernel is 1 plus 2 times that sum. Let's see. Sum from 1 to n, cosine nt. And when you think about what that is, that's 2 times star minus 1. Because my star would have a 2 in front of it. My star starts with 1, so that would be 2, but I have a 1. So if I give myself a 2, I have to subtract a 1. Okay. And when you put that all together, you get 2 times that thing I just calculated, minus 1, turns out to be the Dirichlet kernel. Check. Interesting, that looks nasty at t equals 0, but it's a simple matter to do L'Hopital's rule. L'Hopital's shows dn of t tends to, let's see, you differentiate the top and the bottom and then let t be 0. What do you get? N plus a half cosine 0 when you differentiate sine n plus a half. And on the bottom, you'd get 1/2 cosine 0. And so you get that this goes to 2n plus 1, which is something big. So the Dirichlet kernel gets big at the origin as t goes to 0. So in fact, you can define it to be 2n plus 1 at the origin. But the important thing to note is that is big, which means that Fourier series are going to be interesting to analyze because there's going to be something big happening at the origin in this thing. Let me graph it. It's a pretty graph to look at. I should have fired up Maple to get a really pretty graph, but let's see. It's really big. And the next humps are smaller, 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 like that. And it's symmetric about the origin. Like that. And this is a big thing, 2n plus 1. An important key property, one of the key properties of the Dirichlet kernel, is that even though it looks like it's pretty wild, the integral, if you add up all the areas, plus and minuses of the areas under those humps, is that the 1 over 2 pi integral from minus pi to pi of the Dirichlet kernel dt is 1. We can see that now because of the integral of all those wiggling sines and cosines terms are 0. And the 1 that sits there in the middle, integrates to 2 pi. So 1 over 2 pi times 2 pi is 1. And the cosine, all the cosine things integrate out to 0. So that's easy. Integral from minus pi to pi of the cosine nt's dt in the star expression are all 0. Let's see. What else can let's see. Here's some nice words to know. Remember, when I had a Fourier series for f, and I take a finite sum in the Fourier series, that's a naught plus a sum as n from 1 to capital N, an cosine nx plus bn sine nx. Remember when I, last time, I showed you that that sum is equal to the sum as n goes from minus capital N to plus capital N of Cn e to the inx. This is called a trigonometric polynomial by tradition. So a trigonometric polynomial is something that looks like sum minus n to n, complex number. Doesn't have, yeah, so this would be those were the coefficients, but I could put any complex number here. So complex numbers. That's the definition of a trigonometric polynomial. And we show that this thing is also can also be thought of as a trigonometric polynomial. So I guess that's called a trigonometric polynomial, and this is also called, because they're equivalent. And they turned out to be pretty useful and important in lots of places. And I'll be saying more about the relationship between those two things as we try to get a cleaner, shorter, nicer formula for a Fourier series. It's really important to do that because we want to analyze convergence. And we know those formulas were so ugly it would be agony to deal with them. And it was Euler who discovered clean and nice ways to do it. And then it was up to Dirichlet to figure out how to make those formulas useful. So that's the plan. So you should be reading Stein chapter 2. Now to understand what that's all about. Any last minute questions about anything? Okay.